Last problem. It's an Opamp first order problem. Looks like this. The question is, find V naught. So your first step, predictably, is the same as your first step in any first order circuit. So take a look at it and see if it indeed it is a first order circuit. It is. There's just one capacitor in it. Is it switched DC? It is. For time less than 0, it's being driven by 1 voltage. For time greater than 0, it's being driven by a different DC voltage. So you can use the first order plug and chug technique. So we begin by drawing it for time less than 0. And our goal, even though we're asked to find V naught, is not to find V naught. But our goal is to find VC. And so to do that, we have to first redraw this for time less than 0. For time less than 0, for any time less than 0, U of t is 0. So 2 times 0 is 0. So this entire voltage source for time less than 0 is just a constant 3-volt source. And of course, since we're in DC steady state, our capacitor is open. We still have to draw the open part so we can draw our VC, which is what we're trying to find. Again, if we wanted to, we could analyze this for all sorts of interesting voltages and currents, but the only thing we care about, this whole circuit, is just VC. Don't be the person on the test who says, I don't care that we should be finding VC for time equals 0. I'm going to find something else. Don't do it. Okay. Okay, so the golden rules for op amps. There's just 2 of them. The first is no current goes into it. Now you can have current coming out of it, but no current can go into it. And right, that seems to violate KCL, right? That the sum of the currents has to be 0. So if no current goes in, no current can go out. Yeah, so what's really going on is this thing is being driven by an external source that's not being shown. And that external source is what's allowing current to flow out. But there's no current that ever goes into either the positive, the inverting, or the non-inverting. Maybe a better way to write that is to say I plus equals 0 and I minus also equals 0. The second rule is if there's negative feedback, and there will always be negative feedback, then your input voltages will be the same, because if they're not, the output will swing wildly to make it so. So these are the golden rules for op amps, and they will help us analyze this circuit. So let's see what's happening here. There's negative feedback, so therefore this voltage is the same as this voltage. Now, what is the voltage at V plus? You can see the voltage at V plus is connected to our ground wire. So this is going to be 0 volts. And that means that this one also has to be 0 volts as well by rule 2. All right. We're not sure exactly what's going on. We can see that we're going to be using this 0 volt thing here. Whenever you get confused about op amps, always think about doing KCLs at the inputs. Never at the outputs. Never at the outputs, because you don't know what current's coming out of it, but you sure know what current's going into it. It's going to be 0. So let's do a KCL someplace over here. We could do a KCL here. Not super interesting since we know it's 0 volts. Or we could do a KCL here, which is very interesting because if we call this ground, which is a reasonable place, then we've already named this node. It's VC. So let's try doing a KCL up here. We could also have tried a KCL here or a KCL here. Can't do a KCL here at the output. But let's try a KCL here and just see if we get anything. VC minus 3 over 10. That's the current going in this direction. And now we'll do the current. So that's this current. And now we'll do the current going in this direction. That would be VC minus 0 all over 2. And that's it. Those are the only currents, equals 0. So we just sum the current in that direction. That has to be equal to 0. And a quick check says, yep, I've got one equation, one unknown, and I can solve for my VC. So that's how I'm going to do it. Now, what would have happened if you accidentally did something else? What would happen if you had tried doing it over here? Let's just check that out, and then we'll erase it really fast. Doing KCL here, the voltage going this way would be 0 minus VC over 2. And then the current going this way would be 0. And then the current going this way would be 0 minus V0 over 24. And all that is equal to 0. Okay, that's a valid equation too, but the problem here is that we've got a VC and we've got a V naught. And so that doesn't give us enough information to solve for VC. It just gives us enough to find VC as a function of V naught, which is not what we want to do. So let's not do that. And just to round things out, what would happen if you tried to do it right here? You could figure it out. This current, it's 3 minus VC over 10, but you would not be able to figure out the current going through the 3 volts. So it wouldn't help you find what VC is. You know what the voltage is here, but you don't know the current. But this thing will work, so let's simplify it. Let's multiply through by 10. That would give us VC minus 3, multiplying this by 10. Multiplying this by 10 would give us 5 VC, and all that equals 0. So that gives us a total of 6 VC equals 3. And that means that our V naught, our VC at time 0, is going to be 3 over 6 or 1/2. And that's our answer for step 1. Step 2, but for time greater than 0. And our goal here is to find tau. Even though we're asked to find V naught, I'm just going to put this in red. We don't care what we're asked to find, we're going to find tau. So for time greater than 0, this whole voltage boils down to 5 volts. Since for time greater than 0, U of t is 1, 2 plus 3 is 5. And it's pushing through our 10 ohm resistor. And we've got our capacitor over here, and we've got our 2 ohm resistor here, and this op-amp here. And our goal is to find what impedance this capacitor sees. Now, when we're talking about impedances, we zero all of our sources, all of our independent sources. I'll just write that down. 0 all independent sources. Of course, now we're just left with this dependent source over here. We don't know what it is, so we're going to have to replace this with a test voltage or a test current. You can do either one. For op-amps, it's always better to use a test current. And you can put that test current in either direction, up or down, but you've got to use active sign convention. If you were going to use a 1 amp test current, you've got to always use sign convention, active sign convention, since it is a source, to write down what your V test is. And then we're going to say that our REQ is equal to V test over I test, which is 1. And now that we know the R test, the R equivalent, now we can plug it into our formula for tau. So this is how we're setting things up. If you put your test current in backwards, it would also work fine. You just have to invert the direction of your V test, and you'd get the exact same answer. So we need to find out what V test is. And we're scared because it's an op-amp. And that does look scary. And the only thing we know is that there's no current that goes in. And we know that this is 0 volts since it's connected to ground. And we know that if that's 0 volts, this also has to be 0 volts. And we said that there's something magical about doing KCLs. Now, we could do a KCL here. I worked it out before, but we're going to have a term that's in terms of V naught. This 0 minus V naught over 24, that's going to be this current. And we really don't want to get terms in terms of our V naught. We want to have everything in terms of just our VT. Let's do our KCL again here. Now, if this is ground and if this is VT, then this node is already termed for us. It's already VT. So there's only one place that we are interested in doing our KCL. It's up here. And let's do it the same as we did before. This current going in this direction is going to be VT minus 0 all over 10. And again, that is this current. This current is VT minus 0 over 2. And then the current going down is negative 1 amp. And all that has to be equal to 0. So let's multiply through by 10 to get rid of some of these fractions. Let's multiply through by 10 to get rid of these fractions. And we get VT plus, let's see, times 10 would be 5 VT equals, times 10 would be minus 10. We'll move it over to the right, and that equals 10. So this would give us 6 VT equals 10, which is the same thing as saying 3 VT equals 5, or VT is equal to 5/3. And now that we found the equivalent Thevenin voltage, I'm sorry, now that we found the test, now that we found the test voltage that exists when we put in a 1 amp test current, we know that the equivalent resistance is equal to, by Ohm's law, the test voltage over the test current. And the test voltage we just said was 5/3, and the test current is 1. So that means that the test resistance, the equivalent resistance is 5/3 ohm. And our goal is to find tau, which is Req times C, which would be 5/3 times 1 over 40. So 5 goes into 48 times, and so that's 8 times 3 is 24. So 1/24 of a second, this thing undergoes 1 time period's worth of discharge. Step 3 is to evaluate it at time equals infinity. So at time equals infinity, we have 5 volts in, right? Because this is 2 plus 3 is 5. Here's our V of infinity right there, 2. And now we've been around this road enough that we can kind of see what happens a lot. We can see that there's more stuff over here, but we can see that this is 0 volts. Therefore, because there's negative feedback, this has to be 0 volts. If you want to find out what V of infinity is, we can see we want to do a KCL up here, and that gives us V of infinity minus 5 over 10 plus V of infinity minus 0 over 2, all equals 0. Multiplying through by 10, it gives us V of infinity minus 5 plus 5 V of infinity, all equals 0. So that says 6 V of infinity equals 5, and therefore V of infinity is equal to 5/6 volts. So now we're almost done. We can plug this into our equation, and we can say that VC for any time t greater than 0, it's always going to be our V of infinity plus V0 minus V of infinity times e to the minus t over tau. Just check. I did that from memory. Let's see if it's right. At time equals 0, this goes to 1. So it's as if the exponent has turned into 1. E to the 0 is 1. So the V of infinity is canceled, and we're just left with V naught at time equals 0. That's right. For a really long time, this goes to 0, and we're just left for V of infinity. So I remembered it right. So we can now plug in 5/6 plus, let's see, we start off at a half minus 5/6. That's 3/6 minus 5/6. So that would be minus 1/3 e to the minus t over tau. And tau is 1/24. So 1 over 1/24 is 24. And so this is what our voltage across our capacitor is for time greater than 0. Again, we just took this number and this number and this number and plugged them into our plug and chug equation to find that. I should probably also give the units here that it is all volts.